When we write a thermochemical reaction, what we can do is either include the heat as part of the reaction itself, or we can specify the heat off to the side. Now let's take a look at a couple ways that that could work. We can think of it like this. If I have 2 moles of liquid water, and we add this much heat, 572 kilojoules, we can end up getting 2 moles of hydrogen gas and 1 mole of oxygen gas. In other words, we've added enough heat that we've actually popped apart the bonds and had new bonds form on the other side. Now you might say to yourself, well, wait a second, shouldn't that not work? Shouldn't it just evaporate? Possibly, but remember, we're talking about a thermochemical reaction. We aren't necessarily going to look at all the steps that are in between. Maybe this did go from liquid to gas first. Maybe then we used a different amount of heat. From the heat, we were able to pull apart the bonds, and then we reformed bonds, and then had everything cool down to remove the amount of heat that we had arbitrarily added, other than this. And look at the difference. You could come up with schemes to do this, but that's not really the point of this one. We can write it in like this. I'll point out that if I reverse the reaction, I'll have the exact same thing, but in reverse. And the heat will always end up being along with the water, because it's going to be either a reactant along with water, or a product made along with water. Now, we can think about whether or not it was going into the system or exiting the system from this. So in this case, notice that we had to put heat into the system. So this top one would be an endothermic reaction. The bottom one would be an exothermic reaction. So with that, we can actually fix our signs if we wanted to, and we can write it off to the side instead. So we can see here in our endothermic reaction, we wrote it as having a plus sign, and we just wrote it as being separated off to the side. And in the endothermic reaction, we did the exact same thing. Because it's exothermic now, we had the sign flip on us to be a negative sign of the same magnitude. Now, here's the key thing I want us to remember, though. These are going to be part of the balanced chemical reaction. Even if we write them off to the side, it's still going to be part of our balanced chemical reaction. If we increase the amount that we're using, that does not in any way change your stoichiometry. This is going to be the enthalpy of a reaction. If we then want to find out the amount of heat energy that was given off, what we would do is we'd use our stoichiometry in order to calculate that. So what I'd like you to do is pause the video and try this question out at the bottom. If 10 moles of H2 gas are burnt, what is the delta H of reaction? And I'll give you a hint there as well. If you burn a kilogram and 10 kilograms of octane, do you get the same amount of heat energy from them? Go ahead and pause the video and give it a try. Okay, now if I take 10 moles of hydrogen gas, I'm going to convert it into hydrogen gas here. I'll assume that oxygen is my excess reagent. Now from that, I'm going to be making heat energy as a reactant, or I can just think of it as I'm running the reaction in this direction, this is what I'm giving off. Notice the minus sign tells me it's being given off. So 10 moles, I divide by 2. So I'm going to have 5 times that I'm running the reaction forward. 5 times that, so it'd be 5 times that gives me 0, 35, 36, 25, 28, 60 kilojoules. It's going to have a negative sign telling me that it's exiting the system. Now, of course, you probably did that with a calculator. I just didn't feel like pulling that up in the program right now. But that's how we would do it. Or we could set it up as a fence post problem, where we'd have our 10 moles rather, of H2 gas. Our stoichiometry tells me that I'm using 2 moles of H2 gas for every minus 572 kilojoules of heat that I'm generating. This cross cancels. I end up in kilojoules here, and you can see that all we did is just walk through it the exact same way as I just described. So that's how you'll want to do these calculations. Keep in mind that when you change the amount that you're reacting, you do not change your stoichiometry. However, you do it just like any other problem, where you work it in, you work through the stoichiometry, and you determine the amount of heat that you've produced in the thermochemical reaction.